Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at functions and maps. So we talk of maps between two sets. It's basically just a path from one set called the domain to another set called the codomain. So each of these numbers here is called an element. We map elements from the domain to elements of the codomain. So just a bit of terminology that always comes up. The range is a subset of the codomain. The range is the set of elements in the codomain that are actually mapped to. So if I was asked to write the domain and range for this mapping, for the range, I would just include A, B, and C, not D, because nothing maps to it. And for the domain, we're using these squiggly brackets to indicate a set. All of the elements are mapped, so I will write them in. So we're interested in when a map constitutes a function. So a function is a special type of map in which each element of the domain is mapped to only one element in the codomain. That's why this is a function and this is not. This map is not a function because one is mapped to multiple elements in the codomain. So let's look at a more precise definition. So a function is a map such that each element of the domain is mapped to only one element of the range. Basically, a function means that one input yields one output. These elements in the domain are the inputs, and the elements in the range are the outputs. So functions are very important in things like computers because we want to input something and have only one output, not have a raft of possibilities. So it turns out that if we have a function, we can write it using fx notation. Fx is normally followed by a rule like x plus 2. So fx equals x plus 2 is a function. So it maps an element to two more than that element. So 0 would get mapped to 2, 1 would get mapped to 3, and so on. It's clearly a function because each time you input a value into this expression here, you get only one output. If I were to put in 9, I would get an output of 11, only one output. So this number here is the output in fx notation. If I want f of 1, it just means the input is 1. It just means I replace x with 1. So I take this expression here, everywhere I see an x, I replace it with 1. So the output would be 3. So this notation just tells us that this is a map from the real numbers to the real numbers. We have inputs that are numbers that you know, the input is a number and the output is a number. So if I look at this whole function, not just the bit I showed you down here, the domain of this function is all real numbers. So x is an element of the real numbers. In interval notation, we would write it like this. X can be any value between negative infinity and infinity. These round brackets means we're not including these two endpoints. So it turns out the range for this, as it is for all linear functions, is also any real number in interval notation, any value between negative infinity and infinity. This makes sense. If you have a rule like this, you can input any number you like, but also for the range, any number is a possible output. If I give you a number like 5, you'll always be able to solve the equation 5 equals x plus 2. All right, let's now look at the vertical line test. Another way to determine whether or not a map constitutes a function is to look at its graph. Now, you would be familiar with graphs. They are just maps between sets. The first set, the domain, is the x values, so real numbers, and the second set is also real numbers. We call these the y values. This is the codomain. So if you have a graph, how do you determine whether or not it's a function? Well, you use the vertical line test. So when you're applying the vertical line test, you're asking, is it possible to draw a vertical line that hits the graph more than once? So for this function here, you'll see that the answer is no. No matter where I draw a perfectly vertical line, it will never hit the graph more than once. So if it's not possible to draw such a vertical line, we say that it passes the vertical line test and it is a function. On the other hand, for this graph here, I could clearly draw vertical lines that hit the graph more than once. Only one such vertical line is required, and that graph is not a function. This here is not a function. If it's not a function, we just call it a relation. So what the vertical line test is doing is checking if there is a case where one x value is mapped to multiple y values. So if I return to this one here that is a function, its domain here is x is all real numbers, and its range is y is all real numbers. We can't display all real numbers on the graph, but these arrows means it goes forever in that direction. So this graph shows that we can have any input we like and any output we like. Once again, if I wanted to write this in interval notation, it just write it like this, which means that both x and y can take any value between negative and positive infinity. So let's now look at finding the domain and range for harder functions. So let's consider these two functions here. We know they're functions because they can be written with fx notation. We're going to look at the domain and the range. So the domain is the set of inputs. It's the set of values that x can take. So you can square any number you like and add 4 to it. So that's why the domain here is negative infinity to infinity. What about the range? Is it possible to have any number as an output? So it's actually not. For example, if I wanted to solve the equation here, 0 equals x squared plus 4, I can't do it because I would get x squared equals negative 4. We can't have x squared equals negative 4. That proves that 0 is not a possible output of this equation here. So why is that? Well, remember that square numbers have to be non-negative, 0 or positive. So we need to have that x squared is positive. Adding 4 to both sides, we get x squared plus 4 is greater than or equal to 4. I've just shown that the outputs here must be greater than or equal to 4. So we can write the range as y is greater than or equal to 4, or we can write it as 4 to infinity. I use a round bracket here. We're not including infinity because you can't actually equal infinity, but I'm using a square bracket here because I am including 4. Y can equal 4. So if you choose a number less than 4 and substitute it here for fx, noting that y and fx are the same thing, if I do that, I won't be able to solve the equation. So only numbers greater than or equal to 4 are possible outputs here. So what about this here? Let's look at its domain and range. We have to start looking at where things might go wrong. Well, you can't divide by 0, so straight away x equals 0 is not part of the domain. You also can't square root negative numbers. So we need to have here that 1 over x is greater than 0. And that implies that x is greater than 0. If the top number's positive and the bottom number's positive, the whole thing will be positive. So our domain here is that x has to be greater than 0. It can't equal 0 because then we'd be dividing by 0. X can't be negative, then we'd be square rooting a negative. So we write our domain as x is greater than 0 in interval notation, 0 to infinity. We're using the round bracket here because x can't equal 0. All right, so what about the range here? Well, when you square root a number, the answer is always positive. Like the square root of 9 is 3. It's not negative 3. So straight away here, we know that y has to be greater than or equal to 0. Remember, y and fx are the same thing. So can we have y equals 0? Well, the only way we could have y equals 0 is if we were square rooting 0. Well, we can't have this equal to 0. There's no number you can divide 1 by to get 0. So I'm going to update our range, so y has to be greater than 0. And once again, in interval notation, it will be 0 to infinity, not including either value. All right, one last thing. Let's look at odd and even functions. So a function is said to be even if this rule holds. A function is said to be odd if this rule holds. So firstly, we're going to look at determining whether a function is odd, even, or neither from its graph. So if the function's even, it's symmetrical about the y-axis. This graph here is symmetrical about the y-axis, and so it must be an even function. So a function is odd if there's rotational symmetry about the origin. This has rotational symmetry about the origin. If you rotate 180 degrees about this point here, the origin, you will get the same graph. So that's how we can tell that this is an odd function. This function here is neither symmetrical about the y-axis, nor does it have rotational symmetry. Accordingly, it is neither even nor odd. Now just note, functions are never even and odd. They're one or the other or neither, but they can never be both. All right, let's look at determining whether a function's even or odd just from its function. So let's look at this here. So the definitions we have up here involve f of negative x. So I'm going to substitute negative x. What that means is I'm going to take my expression and I'm going to replace x with negative x. So it turns out negative x squared is the same as x squared. That holds for any number. You know that. You know that 4 squared is the same as negative 4 squared. Or 7 squared is the same as negative 7 squared. So this is actually just 8 minus x squared. Because we have a case here where f of negative x is the same as f of x, this must be an even function. And it's no coincidence that the only powers of x were even in this function. That's why they're called even and odd functions. On the other hand, if we try that trick here with this function, so I'm going to substitute x for negative x, I get 8 minus, or replacing x with negative x, minus x. So we discussed before that negative x squared is the same as x squared. But these two negatives here, they will make a plus. You can see that this here is not the same as f of x. Because f of negative x doesn't equal f of x, this function is not even. Is it odd? Well, it's not odd either, because this isn't the same as negative f of x. Negative f of x would be negative 8 plus x squared plus x. We don't have that here, so it turns out that this function here is neither even nor odd. And in fact, most functions you encounter will be neither even nor odd. All right, thank you so much for tuning into this video. Sorry it was so long, but this has been the luckiest maths teacher in the world. Have a great day.